Let's continue with our series of electronics, and our series are the electronics, a few things in electronics. And last time when we met, and I talked of the Kirchhoffs and said that Kirchhoffs laws and how to use them to find the current in a circuit and other things like the voltage, the potential difference across the circuit. I said it was a piece of cake, and some of you said, please, there is nothing like a piece of cake. It may seem a piece of cake to you, but to us, it is something that we need to understand. And I agree, and that means that I have to listen to the people whom I'm supposed to be serving. Otherwise, I would be useless. So, in a way of respecting the your wishes, last time I looked at the Thevenins, and this was like the theorem highlighted as, it came as an opening for the series of electronics, the electronics series that we are going to be enjoying. So now I have to look at the Kirchhoffs. And for Kirchhoffs, we shall start with the statement. There are two laws. There are two laws called Kirchhoffs laws. Most people write Kirchhoffs in a wrong way, but this is the right spelling. So these Kirchhoffs laws, there are two of them. These two laws, we have one concerning the current, and the other one concerning the voltages. And today we're going to look at these two laws and then apply them. After, understanding them, then we apply them on a circuit to find the current. So let's start with law 1, which is the current law. It is called KVC. So this one here is Kirchhoffs current law, KCL, and this is Kirchhoffs voltage law, KVL. I can put it in a summary way here and try to make it look a bit more elaborate. So KCL is short for Kirchhoffs current law, Kirchhoffs current law, and then the other one is KVL, which is Kirchhoffs voltage law. In full, we shall have this as Kirchhoffs current law. So these are the two amazing laws. Once we know how these laws work, then life becomes a bit easy. It becomes very easy. The key thing here is the current, and here is the voltage. So let us now state them And once we have stated them, we shall use we shall do three things. So the three things we shall do three things in order to understand these laws. We shall have a statement of the law, statement of the law. So we shall have a statement. After having a statement, we shall have a explanation. Explain how what this law is all about, how it comes about, and then have a small comment. Have a comment. Comment. What is it? What is it all about? How does it come about? What does it, in a way, signify? So, I will have to. Oh, we are together in this. So, I'll have a stating the. For example, we are going to state the current law. After stating it, explain it, and comment on what makes it this law. And so first thing first, we look at the statement. We start with Kirchhoffs current law, and then we look at the statement. The statement is that it's all about the current. So we shall say that the algebraic sum of currents entering a node or branch point is equal to the algebraic sum of currents leaving the node or branch point. Very heavy. It looks heavy. It looks a heavy statement, but that is the statement. The statement is that, to state this, the statement is that the keywords here are mainly algebraic. The word algebraic means that if entering was to be positive, then leaving would be negative. A current entering a node or a branch point, that current entering, if entering a branch point is taken as positive, then leaving a branch point or a node. When we talk of a node, is like if the wires, if this is a wire, and then you join other 2 wires or 3 or 4, this is what we call a node. This is the node here. We are gonna understand this. So this is the node. A node is a branch point. So a branch point, no one is seeing this, so I will put it a little bit here. So if we have a current or a wire having current flowing in it, and then at some point there is a junction to other different wires, 2, 3, 4, if this was I1, this is the branch point. This is the node where they meet and they eventually get out. The key word here is that if entering here was to be taken positive, then leaving this branch point, we shall take it as negative. And that is the idea of algebra, algebraic sum. If we can sum all those which are entering, that will be equal to the algebraic sum of those which are leaving. So the ones which are leaving will be negative if the ones entering are taken as positive. These ones will be negative. It's algebra. If we go to the Form 1 algebra of the number line, whereby when you are moving on a number line, if this was our number line, this being our 0, if this going to the right is positive, then going to the left would be negative. This, if you take steps to the negative, would be negative. Negative 2, negative 3, and this would be the origin or the reference point. So similarly, in when we are dealing with this law of Kirchhoffs, we say that when we are going to the positive, when we are entering a node, we shall take that as positive. Remember, these are laws. When it is a law, it is a law. Lawyers know this very well. It's a law. You got nothing to do about it. You follow the law. It is quoted. Lawyers quote the law. Then they, after quoting it, they look at how they argue. They make an argument of how this law is applying to your case, and then eventually the judge decides that the argument is good enough. In physics, it's a law. We follow it, we use it, we get to solve other problems. If you bring your, I don't want to call it a big head, but if you bring in your argumentative mind in physics, then you'll have problems. Because, for example, current people met and agreed that there is a conventional direction of current. If you're gonna come in and want to now change that and look at it differently, that's your problem. You'll have a field day in getting to know that. So, statement, we have gotten the statement. Now I've been trying to explain, but I want to explain it better and state it here so that you are able to see it. But we shall look at these laws in 3 phases. We do the statement. After doing the statement, we do the explanation, then comment. We now look at the explanation. Explanation of KCL. Kirchhoffs current law. So the explanation is that if we have currents, take currents IK where k equals to 1, 2, 3, and so forth. Then because the ones entering would be equal to the ones getting out, we shall have the summation of k equal to 1 up to n of them. Ik would equal to 0. Never mind about this kind of mathematics expression. We are saying that if we have I1, I2, I3, and then some are entering, some are leaving. So if this was our I1, for example, this is our node, which is the same as a branch point, and then we have currents branching off as I2. We have another one entering here as I3. We have another one leaving here as I4. Then we would say that those which are entering, I1 plus I3, because these are the ones which are entering the branch point, this one here and this one here are entering the branch point. So then we have these equaling to the ones which are leaving, I2 plus I4. I did not intend it that odd numbers become entering and even numbers become leaving. I don't want you to get it that way, that if you have odd ones, they will be entering, and then the even one, the even ones will be leaving. Not really. So if that is the case, we can, if algebraic sum means that we are having the I1 plus I3, or we can write them in the order in which they are. So plus, if those entering if these entering here are positive, then leaving being negative, so we shall say plus I2 negative plus I3, which is positive because it is entering, then plus minus I4 equals to 0. This is where the idea of the I1 plus I3 would equal to I2 plus I4, and the concept of the algebraic sum, the algebraic sum entering equals the algebraic sum of the currents leaving the branch point. And so this is the explanation of this Kirchhoffs current law. So we shall, now that that's the explanation, so it means that current which is entering this point equals to the current leaving. But the question is, what is the current? What do you know as the current? Current is the same as the amount of charge which is going past a given point in a time t. So it's the rate of flow of charge. So the rate of flow of charge in this point is equal to the rate of charge flowing out of this point. So we learn something from this, and this learning, this that we learn from this is what is gonna comprise our comment. So comment. So the comment comes from the explanation we got. The explanation was that the amount of current flowing in a branch point or a node equals the current leaving this branch point or node. But also we say that the current is the rate of flow of charge. So if the rate of flow of charge entering a point equals the rate of flow of charge leaving the point, so we can comfortably say that this So we can comfortably say that this is the conservation of so we can now comfortably say that this is the law of conservation of charge. So because the charge that entered the node equaled the charge that left the node. So this is the law of conservation of charge, that the amount of charge that entered the point equals to the charge that is leaving the point. And so this law is that charge never gets lost. Charge is neither destroyed nor created. It is always there. So when you either charge by induction or any other method, you are just trying to separate charge. You are not going to be creating charge that I created charge. You are not creating charge. If you are charging a battery, a car battery, you are just trying to, if it is a lead acid battery, you are trying to just separate the anions and the cations. And once they are separated, a potential is created across the gap, okay, they across the electrolyte, and once you connect on the two electrodes, the lead and copper, then you have the charges flowing, and then they constitute a current, and then you use it. After using it, then you need to charge it. If it is a car, it is continuously, the dynamo, okay, the alternator is continuously charging the car battery. Once you stop somewhere and you are trying to play music and light, if you forget on your lights, and or you play music and you are happy to enjoy music, then eventually you find that your battery is down, because the charges now mingle up, neutralize each other, and your battery gets dead. They say dead, then you have to recharge it once you either put it on electricity, or if you were keen enough, once you feel like now it is getting low, you just switch on the engine, charge it up, and play music again. Let's say if you are camping out with a couple of people. So that is Kirchhoffs' current law. Some people will say law 1, the other one will be law 2, but let's make it more specific. Kirchhoffs' current law. We stated it that the algebraic sum of the currents entered in a node or branch point is equal to the algebraic sum of the currents leaving the node or branch point. And so next, now we look at the voltages. If we have a circuit and it has voltages, it has EMFs, that is the batteries which are providing the voltage, and then across the resistances we are having the potential drops, the PD, so that is also a voltage. We're going to find out how this law works. Kirchhoffs voltage law, Kirchhoffs voltage law, KVL. So we start with the statement. And this statement is so interesting that in any closed loop, the algebraic sum algebraic sum of EMFs. EMFs we mean electromotive force. In electricity and magnetism, this is the work done by non-conservative forces against moving a charge, a unit charge across the electric field of the battery or within the battery. That's the EMF. The work done by non-conservative forces to move a unit charge, that is 1 coulomb, across the electric field within the battery itself. So in any closed loop, the algebraic sum of EMFs, electromotive forces, is equal to the algebraic sum of the potential drops. So I say PDs, and this is potential drops. I will highlight what it is all about the potential drops and rise. So the key word here, in any closed loop, if it is a closed loop means that you have your circuit with some battery which is providing the EMF. You have the resistor, for example, which is across which there is a potential drop. The moment the current goes through, and you have the current, so this one here is the current times the resistance, and this one here is just the EMF. Sometimes when I'm writing it on the board for students, I say nice E. I write it nicely as a nice E, something like this. Some people may confuse it with epsilon. So let me go a bit again, that in any closed loop, the algebraic sum of EMFs, electromotive forces, is equal to the algebraic sum of the potential drops in the circuit, in this loop. So I could have said in this same loop, but we don't need to do that now. But in time you should be able to now, I want you to get this in a more comfortable way. Don't be stressed. It's about laws. Just like the Constitution, you know there is this law, you don't do this, you do this. So when they got you doing this, and then they do it wrongly, you say, no, you are making me not to congregate, but I have a right from Article 1 that I should be able to congregate, something like that. I'm not very conversant with the articles of the Constitution, but I'm just showing you that it is a law. Once you know this law and how it operates, life becomes easy. This is the statement of Kirchhoffs' voltage law, KVL. What is the explanation? How do we explain this? Explanation. The explanation is that if we have a closed loop, for example, we have a battery, this is its positive, this is its negative, and then we have a resistor somewhere, R, and it is a closed loop, and we take this as a loop L. So we have loop L. Then we say that the algebraic sum of the EMFs is equal to the algebraic sum of the potential drops. This is the current that is flowing through our circuit. This will be the sum of the potential drops, which is IR. How does this come about? This comes about from the fact that the amount of power generated by this battery here equals to the amount of this power dissipated in here. So power generated is the same as IE. This should be equal to the power dissipated. Power dissipated. And this should be the same as I squared R. And this is where we get this I and this I here going, and then we end up back with this expression of the algebraic sum of the EMFs is equal to the algebraic sum of the potential drops. Because whatever we generate in this loop here, in this our loop here, whatever we generate is what will be dissipated here. Nothing will be lost, nothing will go anywhere. Whatever you generate is what, when you eat food, you're gonna have to do exercise to use the food, or it will be dumped on your body as fats, and then you'll end up being fat, some fat guy. So this is the second. Whatever is generated within this battery here will end up being dissipated in this resistor here. It could be a lantern, it could be a bulb, a incandescent bulb, it could be a flat iron, it could be a cooker, it could be a pacorera. When we say this potential drop here, this could be any load within this circuit of yours when you are trying to work on. So whatever would be generated would be equal to whatever would be dissipated. And with this kind of understanding here, then it becomes very easy. With our law here being that the summation of the algebra, here it is summation, but we mean algebraic sum. Algebraic is that if we have, this is now what I want to explain. Before let me comment, then now talk about the algebraicness of not algebraicness, but the understanding of algebraic for currents. Algebraic meant that whatever is entering the node is positive, then leaving the node would be negative. How about the EMFs? And how about the potential drops? How do you determine the algebraicness, the algebra in this? But before doing this, let's now comment. Let's comment and then do the nomenclature of what is positive and what is negative in terms of the EMF and in terms of the potential drop. And then we do an example, and I can assure you, you will now find that the statement I said that Kirchhoffs laws or applying Kirchhoffs laws is a piece of cake. Either you comment and you put in the comments under this video that you were right, or I'll be wrong probably. So what is the comment on this? So we look at the comment. The comment is that when everything that you generated ended up being dissipated and nothing is lost anywhere, then we say that this is the law. This is the law of conservation conservation of energy. Do you know what it means? It says energy is neither created nor destroyed, but transferred from one form to another. This is the basis of neither created nor destroyed, but transferred or transformed. One can say transformed from one form to the other. When you eat food, the nutrients in the food end up going to your body, your metabolism, you sweat up, then you feel you want to do something, you go and dig or do something tangible. So, but that is a bit far away from what we are working on. We are working on current and circuits. So here is the deal. When you get a battery, which is most likely, not most likely, but mostly chemical process, there is chemical energy. That chemical energy, when you connect it to a radio, it will end up into sound energy. That sound energy will go into somebody around will be happy, then it starts dancing. The energy, the sound energy now turns into some other, it starts sweating, etc. So it keeps transforming from one form to the other, but you cannot destroy it. So the chemical energy in the battery, the EMF, will be transferred within the across the loads, for example resistor, and cause a potential drop. So this is it. It's a law of conservation of energy. Energy is never destroyed. That's why when we burn stuff, then we can't destroy energy. You can't say I'm going to, and that's why it has been a tough call to, let's say, if you, why you can't say there are people who will be doing a lot of stuff, and some would even get a bulb with the inbuilt battery, and then they start planting it on a piece of banana plant, and then they say here is free energy. There is no free energy. Energy cannot be created out of nowhere. There must be some other energy you are trying to transform, and it has to be continuously nourished. You can't say I'm going to just be having. You have to make sure you have to eat food to do exercise. If you don't eat food, you will not do the exercise. You will not have the energy to do exercise. We have to put fuel in the car for the car to move. So we put in fuel. The combustion makes the pistons move. The pistons move the tires. The tires, the dynamo, the pistons. Once the shaft moves, the belt moves the dynamo. Dynamo produces electricity. We go in the car enjoying the music. That's how things are. So far so good. We now know to apply Kirchhoffs, we need to know a couple of laws, and we have now known the two laws. Before we actually apply the Kirchhoffs laws on a circuit, an example, a circuit in an example I'm going to share with you, we need to first understand the nomenclature, and that nomenclature will help us a great deal on the part of the algebraic sum. When we talk of the algebraic sum, what do we mean? So let's look at the nomenclature, which is an extension of these laws in a sense. Nomenclature the nomenclature of these two laws. So, but I think mostly this nomenclature is about the KVL, because KCL, simply once you have the current that is entering as positive and leaving as negative, then algebraic sum becomes easy. You label all the positive, all the leaving, okay, all the entering currents positive, and you label all the leaving currents positive. So, but for the voltage, what do we do? So for the voltages, and that is the EMF and the potential drops, this is the nomenclature. So, yeah, so we shall have the EMF, and these are EMFs, and here we have the IR, potential drops. So, and this will be in relation to the, this is going to be in relation to the loop. So for EMFs, if the battery is, because the battery conventional current from the battery I goes through emanates from the positive terminal. If this current is flowing in the direction of the loop, then we say that this one is positive. If the battery, okay, here, so if the battery is having the current coming out of the positive and the loop is opposing that current, then we have this one as negative. The moment you know these two here for the EMF, then you have finished everything. The moment we have our circuit, these are the things to look at when we have a loop. Is the loop we are taking in the direction of the, if it is in the direction of the current the battery is producing, we take that EMF to be positive. If it is opposing the direction of the current from the battery, we take that one as negative. And that's where the concept of or the idea of algebraic sum comes in. For the potential drops, we have a resistor, and then we have a current flowing. So if this is the current flowing in the resistor and the loop is in the direction of the current across the, or from through the resistor, then we say that this is a positive potential drop. And if we have the current coming out of this resistor or through this resistor is opposing the loop, or the loop is opposing this current, then we take this one as negative. Once we know these four arrangements, then that's where I say that, okay, that's why I say that this is a piece of cake. Kirchhoffs' laws is a piece of cake. This is IR. The moment you know if the current through the resistor is in sync in the direction of the loop, then it becomes positive. The current through the resistor is opposed to the loop, it becomes negative. Then the current from the battery is in sync, or is in the same direction as the same direction as the loop, then we have positive EMF. If it is opposing the loop, if the loop is opposing the current I here, then we say that our EMF is negative. And then summing these, taking care of those which become positive and those which become negative, then that's where the keyword algebraic comes in. That you have positives and consequential negatives. So with this, we're now ready for an example. And once we have done this example, you can do many other numbers, and then I can assure you you'll become experts. So let us take an example. We're going to look at an example. And this example is a circuit, and it says that in the electrical circuit illustrated below, B1, B2, and B3 are batteries, each of a nano resistance 1 ohm. So meaning that even the battery itself is contributing to the resistances in form of their nano resistance, what we normally call small r. We use a small r for that. So I will draw the circuit, which you have already seen in a summarized way from the actual diagram. So, but I'll draw it here. Drawing is not my problem. So we have B1, then we have a resistance here, and then we have another resistance here, then also another battery here, and then we have another battery here, the third one. And just wanna make sure that this is the battery here, too big, and then a resistor here. Then I will close in this whole stuff here, like this. So this is our circuit. The better one is shown below. So, but let's now look at a few things inside. So we are supposed to be finding, so this is B1, which is a 20 volts, but we've been told that it has a 1 ohm inside. This is R1, which is 4 ohms. This is R2, which is 4 ohms. Wow. This is 6 ohms. This is the B2, and it is about 18 volts and 1 ohm nano resistance. This is R3 with 2 ohms. And this is B3 with 7 volts, 1 ohm. So in order to find the current which is flowing through R1, R2, so we start by, we can choose this as the branch point and say whichever, because this battery here contributes a current, this battery here contributes a current, this battery here contributes a current. They start flowing. Depending on whichever is speedier or bigger, doesn't matter. Whatever is speedier or bigger will contribute or will determine on the direction of the current. But we can assume our own direction. So we can say this is, for starters, we can take this one as I1, and then we say that it will split into I2 and I3. So this is our node A. We can have a node B, which is, and the rest. So the Kirchhoffs current law at this point is that Kirchhoffs current law is that I1, which is entering here, is equal to I2 plus I3. So this is the first equation that we get. Then we take loops. We can, and we don't need to care. we can just say this is our loop L1. This is a closed loop where you have two batteries and two resistances. And then we can also take another loop L2 where we have also two batteries and two resistances actually, but with also the batteries having these resistances. And then we follow the nomenclature for this KVL. KVL, we follow the nomenclature. And once we follow the nomenclature, we start our business. This loop here, this battery here produces this current. This loop here is in the direction of that current. So this EMF will be positive. The current through here, through the 6, will be in the same direction as the loop. So it will be positive. Here the loop goes down, the current goes down, positive potential drop. Here the loop is going down, the current, there would be current flowing here is going up. But if we consider I2, then we say that it is positive. But the EMF due to this current going up, so it doesn't matter. At the end of the day, whatever, if we get positive I implies that same direction as we assumed. Negative I, opposite direction to the one we assumed. And as I said, it is a piece of cake. So now you can follow the example, the solution, and try it out. Try it, and then following this and see how that comes up. Thank you for following, and if you really want to have this done, the example done, you put it in the comment, and then I will go ahead and do the example. But like I said, this is a piece of cake. So the issue is about the laws and nomenclature. Once you got this, everything becomes simple. Thank you for following and for listening. We catch up on another principle within electronics that people think is so complex, but I make it very simple. You can comment to confirm whether this has been simplified or complicated, or within the comments, and also give suggestions on how, whether I am too speedy, whether I'm too wordy, going astray, explaining stuff, whether I should just concentrate on the principles and chopping numbers, and then we shall be able to work on. But also you can check out my actual in-class video lectures, where I am in class doing my thing, but the camera is capturing me. It may not be so clear, so whatever, because I just wanted some people to see what goes on in a university lecture room. Catch you on the next concept.